All right, well, welcome everybody to High Performance Foam Free Historic Masonry Retrofits. This course is approved for 1 hour in continuing ed, AIA, HSW, GBCI, NARI Green, Certified Green Professional, AIBD, and may be applicable to your local or state-based contractor license. Today I will be your moderator. My name is Brett Little, and I am the Executive Director here at the Green Home Institute. Green Home Institute has a mission to make healthier and more sustainable choices in the renovation and construction of the places we live. And a huge thanks to all of our presenters, our sponsors like Anderson Window, Panasonic, Build Equinox, Sun Intuitive, as well as our members, board of directors, and everybody who supports our work. We couldn't do it without you. So this is a real exciting topic, and I'm real excited to have High Performance Building Supply back again to sort of go off of a similar session that we did back in May. You know, when it comes to foam, foam is has been a fantastic product for the energy efficiency movement. I've personally had spray foam done in some of the homes that I've lived in, and it's just done a wondrous job in rim band joists in the attic. But there are some concerns. You know, at the very basis, just start with the chemical component and makeup of foam. It is a petrol-based chemical, and it's made essentially out of oil. There have been issues with foams off-gassing, putting VOCs into the air and losing their energy efficiency. And there's been foam issues with health and even issues with cost. And when it comes to historic buildings, you're talking about potential, whether they're scientifically based or not, issues that are perceived by historic commissions that foam can potentially ruin buildings. And so we certainly are very excited about this movement of going foam free and doing it in a cost-effective manner. And we're very excited to have Ken Levinson joining us again. He is the CFO and Sales Director of 475 High Performance Building Supply, and he graduated from the Pratt Institute in 1989 and has been a registered architect in New York State since 1993. He's also a certified Passive House designer and a founding board member of the New York Passive House Alliance, I believe, and the National Passive House Alliance, along with the North American Passive House Network. Lastly, Ken is a founding partner at 475 High Performance Building Supply, and again, we're excited to have him back, so take it away, Ken.
All right, thank you, Brett. Very glad to be here with Green Home Institute and all of you attending. First, I would like to, before we dive into the presentation, give you a very brief introduction to our company. We were founded in January of 2011. And we like to say it's someplace where the blower door is king, because air control is the most important factor in making today's high-performance enclosures. And we like to say that foam, particularly spray foam, is not the solution, because we can actually build enclosures that are of the highest performance without it. We can make enclosures that are more resilient and more sustainable. And while we here again, just hopefully again, just to talk for a moment about our company, what we do. While most buildings may not be able to achieve Passive House metrics at this time, we see the clear and definitive goals of Passive House as a guiding star for continual improvement in all the buildings that we work on. We were actually started as a company working on Passive House retrofits and historic masonry retrofits. Project in Westport, Connecticut on the right and Brooklyn Heights on the left. I was the architect, and my partner, Florence Keverling Busman, was helping with the building science consulting and air tightness. Our company is built as an e-commerce business where you can order products and have them shipped directly online. Our website is a source not only of basic resources like specifications, installation, instructions and videos for products, but we've developed a lot of knowledge resources. We include a very active building science blog and a construction detail library to help grow and share successful approaches to robust assemblies. we're very fortunate to partner with some of the leading suppliers from Europe for high-performance products, and we're focusing first and foremost on the enclosures. Proclima is a company that developed out of a serious commitment to building science and building material development and optimizing natural building materials. And they provide a complete approach to air sealing and vapor control, including membranes, gaskets, tapes, caulking, addressing both the interior sides of the assembly as well as the exterior. Bear with me, this clicker here is, with it, we're using solid acrylic adhesives that make possible the most robust and resilient assemblies. Because once you're airtight, you need to ventilate. We're happy to be the exclusive supplier of decentralized high-efficiency ventilation system, the E2 by Lunos. And unlike centralized systems, there's no ductwork or large central machines. Instead, the E2 through-wall units are installed in pairs, one supplying fresh air while the other exhausts air. With each fan running on 1.5 watts, an average heat recovery of 90%, we can have very cost-effective and high-quality ventilation. We're also supplying the only Passive House Institute certified simulated double-hung window, which is particularly useful in historic retrofits and historic districts. Roof daylighting is a subject that is a component that has not been effectively dealt with in the U.S. market, and we're bringing to the market, again from Germany, unit skylights and glass roofs that are truly thermally broken, triple glazed, Passive House compatible. Lightway through roof light tubes, bringing lights to the inside in an efficient manner. And then we also deal with some insulations. We do have a compact foam for thermal break material, as well as wood fiberboard from Gutex, and sheep's wool insulation from Havelock wool, perhaps the most sustainable insulation choice that we can do. I would love to do a presentation perhaps on that someday. Finally, we're happy to bring the Passive House planning package and the Design PH software to help design and build Passive House projects. All right, so that's our company. We'd love to work with architects, builders, engineers, and we certainly hope to work with you in the future and hope you take advantage of our knowledge resources. The task here at hand today, the high performance historic masonry retrofits, and they are foam free, I should add, or substantially foam free. If we can't eliminate it entirely, we do like to eliminate it as much as possible. Here we have some residual AIA slides which we'll flip through, giving the basic course description. We have learning objectives that are applicable across the landscape, talking about what we're going to do. I'll just get into it and do it. Really, high-performance historic masonry retrofit seems like a bit of incongruous. And what do we mean by high performance is really the first question. And we want to first ask it from the user's perspective, that we want the occupants to have a higher level of comfort. We want to have a healthy indoor environment, and this indoor air quality, and this deals also with the lowering the toxicity of our environment. We want it to be very energy efficient. We want it to be resilient. We want it to be done in an affordable way, and of course, we want it to be aesthetically pleasing. We want to maintain the special quality of these historic buildings. So that's from the users looking at high performance, but what about from the masonry, from the bricks themselves? Well, the great architect Louis Kahn might have asked, or as he did, ask, what does the brick want? In our context, we see that the brick wants to be dry, so it can have its full, robust functioning, and it wants to be seen architecturally. It's ornamental. It's a beautiful thing. So between the wants of the occupant and the masonry, it seems that we have an apparent conflict. On the left, where a poorly insulated building is effectively a radiator to the world, the brick is drier, but the building is inefficient and uncomfortable. That building could last forever because it's baking itself dry, but that's incredibly inefficient. On the right, we have continuous insulation around the building, and we have an efficient and comfortable building. But now the walls are colder, and they're going to be wetter, and they're going to stay wetter longer. With brick being wetter longer, we become concerned with freeze-thaw damage and mold damage threats. In looking at the threat of freeze-thaw destruction, it is important to recognize that it is a whole system's failure. Two things need to happen together. The masonry must be saturated, and the weather must be well below freezing for an extended period of time. So one of the questions we'll face here is how do we avoid freeze-thaw and still achieve high performance? We may not be able to control the outside temperatures, but we have a lot of control over preventing saturation of the brick. And this is one of the main places we'll focus. The other threat is mold growth. And the ASHRAE 160P is the basic criteria for mold growth propagation, as it defines it when, on a 30-day running average, relative humidity is above 80%, when the surface temperature is between 41 and 104 degrees Fahrenheit. So even if we don't have a saturation and freeze-thaw problem, we need to be careful that the mold threat is mitigated too. So to mitigate both threats of saturation and mold, we need to always be thinking about how we can increase the drying potential of the assembly. We have a basic formula for the assemblies that across all assemblies that also holds true for historic retrofits, that we want the drying capacity to be greater than the unanticipated wetting. If we maintain this relationship, you'll have freedom from damages. So we're always looking to help the drying, and in doing so, increase the resiliency of these historic structures. Of course, we can avoid the problem altogether by simply insulating outboard of the masonry, putting it within the thermal envelope. The brick will be heated as part of the interior conditioned space. It's warm and dry. But while it's often preferable to wrap the exterior from a building science perspective, often we don't want to from an aesthetic perspective, and growing historic preservation districts often simply won't let us. So today, we are assuming we can't wrap the exterior of the building. We are looking for robust solutions to make a high-performance building while insulating from the interior. Or simply put, how do we avoid saturation and mold while maximizing comfort? There are 5 basic parts to the solution we will focus on here today, followed by a walkthrough of a real-world case study. First, as with any building, we must successfully shed water, and it is especially important in historic masonry structures. Second, we want to maximize the air tightness and vapor control. And in doing these things, we also maximize the drying potential. Third, we want to maximize safe insulation levels, and the key word here is safe. And the big question is how much insulation can we put on the interior side of the masonry and still avoid problems? Fourth, we want to install great windows. Windows are the biggest envelope holes and threat to efficiency and comfort. Putting great windows fully integrated into the structure, we want to leverage the comfort and efficiency benefits of high-performance windows. They're a huge asset to the overall performance. Fifth, we want to install great ventilation. We want to build tight and ventilate right, as the saying goes. Balanced, distributed ventilation with high-efficiency heat recovery helps provide high-quality indoor air. So shedding water is job 1 to avoid saturation and freeze-thaw. Often where freeze-thaw is detected, there is a breakdown in water management. Here are 2 examples. On the left, although it appears to be an abandoned building where all the brick gets to freezing temperatures, the brick is in otherwise good shape. Where the damage is occurring is where the downspout is broken and the brick is being flooded. Sort of unavoidable saturation at that point. On the right, we see damage below the windowsill. Here the sill is a rowlock of brick without strong flashing, a strong flashing detail. The sill of a window will see the highest concentrations of water as the glass above isn't absorbing any water. So here are two good examples of avoidable problems. So we need to make the drainage function properly. We need to fix, restore, replace gutters, leaders, and drains. We need to move water away from the surface, repairing and replacing cornices, sills, flashings, and drip edges. Putting these items in good working order goes a long way to avoiding the damages we want to. The next part of shedding water is to verify the porosity and quality of the bricks. Even face brick, meant for outside exposure, can have a wide range of quality. Conduct a visual and physical inspection first. If there are concerns about porosity, we can do a variety of tests. One can do Karsten tube tests, quick on-site absorption test that's readily available, shows how slowly or quickly the brick is absorbing the water, shown on the left. If there are questions beyond this, full immersion saturation tests can be performed in a laboratory that are more scientific if we feel the risk is there. We want to generally try to avoid coatings on the outside of the brick, but it may be necessary. So all part of this inspection. And we need to, of course, inspect and repoint as necessary and replace masonry units as necessary. In this manner, it's important to replace the mortar with a soft mortar mix. The mortar is a sacrificial layer. On the right, we see the bricks acting as the sacrificial layer where the mortar is staying in place. This is the wrong mortar mix. There are soft mortar mixes available. We're showing from the New York City Landmarks Preservation Commission, has some great resources. You can Google it pretty easily and find them. So let's look at a couple of water shedding failures that led to freeze-thaw damage. First, at the roof here, this coping failure at the parapet is leading to saturation and freeze-thaw. But the freeze-thaw is not because of insulation. The parapets are always cold. Here, water shedding failure at the top of the wall is where the roof was gone, leading to saturation and freeze-thaw. When we see freeze-thaw damage at tops of buildings, we can't assume it indicates a universal condition. Oftentimes, these shedding problems and the damages are usually localized. The rest of the brick below here is in okay shape. We see this in many masonry buildings that have been abandoned. The bricks are certainly freezing over the winters, but it is really, again, where we have faulty shedding of water that saturation and freeze-thaw becomes an issue. We also have to deal with rising damp. Masonry is a sponge for moisture from below. Sucked up into the thermal enclosure, the wet and dry cycles can lead to damage with uptake of ground salts. So we want to provide interior and exterior drainage, whether it's with the pitches, drain mats, perimeter drains, sump pumps, whatever the particular situation demands and or allows for that matter. We want to install water barriers, plastic sheets, waterproofing membranes, capillary breaks. All of these things, depending on the situation, may be useful and necessary. Here are more examples of the drainage mats and the capillary breaks. So we've talked about shedding water and about avoiding saturation. Now we want to turn to the second thing, which is air tightness and vapor control. We like to say that air control is more important than thermal control. because it disproportionately affects 4 basic functions of the building. First is indoor air quality. We need to be able to control the air to control the quality of it. And the only way you can really have control of the air is in an airtight environment. With greater control, the mechanical systems can be smaller while ensuring very high quality. Second, comfort. Drafts are a leading cause of discomfort and need to be overcome with mechanical systems typically. Third, thermal bypass. Through air infiltration, convective loops, wind washing that degrade the insulating values by as much as a factor of 5, resulting in completely different performance to that enclosure. And last, but perhaps most importantly in this regard, in what we're talking about today, is the air transported wetting. Air leaks and air transported wetting are the biggest liability after bulk water, a much bigger liability than vapor diffusion, which is what folks often think of first. Here we have a diagram on the left from the Building Science Corporation showing 2 sheets of gypboard. The one on the left, we have vapor diffusing through that gypboard into the assembly over the course of a winter in a cold climate. We see 1/3 of a quart of water diffusing through. That same piece of gypboard over the course of the winter with a small air leak is transporting 30 quarts of water, that indoor humid air, to the enclosure. So we have a geometric difference in the liability to the wall and the possible damages. In historic masonry constructions, we also have ready-made points of air infiltration, as shown on the right, where floor joists and beams are embedded in the masonry walls. So if we're not air sealed, the danger of condensation grows. At the right, we see the building science diagram showing how convective currents move warm, humid air from the inside to the cold brick and condensing there. On the left is physical evidence of this effect, where humid air circulated behind foam boards where the foam boards were intermittently adhered to the masonry. So you see the spots of the adhesive and the mold growth in between. So we want to not only surround our conditioned spaces with air tightness, the red line, and this air tightness, should be said, must be continuous, accounting for penetrations and intersections. We also want to surround our insulation with air tightness, as shown on the right, protecting it from degradation and maximizing the insulating potential. In doing so, we can essentially gain insulating value without adding insulation, which takes away from interior square footage. Always a concern in these retrofits. For historic masonry walls, surrounding the insulation with air tightness means making the enclosure airtight inboard and outboard. The primary, most important air barrier is inboard of the main insulation layer, the red dotted line. This keeps the conditioned air in the conditioned space. The secondary air barrier is what we artfully call a wind-tight layer, and it is really just preventing the wind from degrading the insulation from the wind washing. The masonry wall itself, in some form, performs this role. We'll get into that more in a minute. To achieve this continuity of air tightness around the building, we have to pull everything away from the existing brick. We need to be a bit ruthless about it. We need to cut back about 6 inches around the flooring and at the ceilings so we can see everything to get at the construction. We basically have a negative donut where you could stand at the top of the building and walk around and see all the way down to the cellar along the perimeter of the building. So we're fully exposing, we're examining, we're repairing, and then we're able to air seal. We want to bring these historic buildings back into good working order. They're all too often buried in renovations and neglected. We need to get behind the renovations, get to the brick structure, and repair the problems. To make the brick windtight, airtight, often repointing and fixing the brick can be enough to get the job done. The best practice, though, is to coat the inside face of the brick with lime plaster, which is vapor permeable as well and chemically helps fight mold growth itself. But what we typically see installed is a permeable liquid membrane at the interior side of the brick, as shown in the middle, like stole gold or emerald coats. Sometimes folks will look to make the brick face the primary airtight layer rather than the inboard, rather than at the inboard side of the insulation. It is typically fairly labor-intensive to do this, and it can be difficult to really get true airtightness, but it's possible. The real problem, though, is that the air barrier is in the wrong place. The conditioned air can reach the cold brick, leading to elevated condensation potential on the inside face of the brick. Cellulose can buffer a certain amount of humidity and help mitigate the problems, but we'd prefer to head off the problems to begin with, if we can. So optimally, we'd like to put the airtight layer inboard of the insulation. Again, keep the conditioned air, the conditioned humid air away from the cold surfaces. This lowers the condensation risk dramatically. So what can we use for inboard airtightness? Drywall has historically and often been used as an airtight layer as techniques have developed over time. It's inboard of the insulation, so it's in the right location, but it's less than optimal for a number of reasons. First, it's exposed to the occupant, so it's taking abuse. It isn't continuous with the insulation. There's a lot of discontinuity, there's a lot of complications, a lot of junctions. It can crack over time. And the bottom line is that the gypsum board, we'd like to say, is a sacrificial layer. And sacrificial layers should not be an essential control layer in the performance of the building. How about spray foam? Well, we have a bit of a lead on this. This is a foam-free historic masonry retrofit. So we could say up front that we're quite opinionated about it, but we think we have a lot of good strategies that show sort of where, when, and why, and what. Spray foam can provide airtightness, but it's problematic on many levels. The ingredients, as Brett was saying at the top of the presentation, are problematic. That's a fire accelerant that can have very high global warming potentials. Ultimately, at the end of the day, and there are certainly many toxicity issues around this, whether for the workers themselves or the occupants of the building ultimately, but the unreliable performance is really what gets us, and that you're basically taking manufacturing onto the job site into very, very highly variable conditions with not super well-trained workforces, typically at least not to the level of complication that a very high-quality spray foam job requires. And so we see a lot of variability in performance. Particularly if we're looking for long-term robustness, this could be quite problematic. We have, needless to say, much more to say about this that you can find on our website. Sheathing, like OSB or plywood, are better approaches. But we should note that we have instances of leaky OSB out in the field. And we need to blog more specifically. You can Google it and see different examples. I think Green Building Advisor has an article out. So you need to be careful with OSB, which manufacturer, the thickness, and so forth. But membranes really are specifically designed for the task at hand. as shown on the left, and are incredibly airtight and really are the most effective way to deliver what we need with that. So with airtightness addressed, to a certain extent, we want to address vapor control as the second part of this. And with vapor control, we're not as concerned about the wetting of using vapor control to prevent the wetting, although it is very important. It's really about the drying of the enclosure. Again, looking at this iconic image, on the left we have poorly insulated building. It's baking itself dry. We're not worried about it from a moisture damage potential perspective per se. On the right, where we have good insulation, we have colder masonry, it's going to stay wetter longer, and it's not going to want to dry out. And the only way it's going to ultimately dry is through vapor diffusion. And so we're always seeing how we can put together the assemblies that are really maximizing the drying potential. We do want to minimize the wetting, but really maximizing the drying potential. So we want to, the big trick is to prevent the wetting and allow the drying. It's counter, it is contradictory. In the winter, the vapor drive is going outward. We want to have an inboard vapor retarder. But we don't want to put up a poly vapor barrier, because we are often air conditioning these buildings as well. And in the summer months, the vapor drive is to the interior, and quite substantially. And it could turn the wall assembly into a quote-unquote swimming pool and have pretty severe water damage due to it. We need vapor variability. We need to prevent the wetting in the winter and promote the drying inward in the summer. So this brings us to the membranes and vapor variability of smart membranes. And what we see on the diagram on the left is this ability to act as a vapor retarder in the winter, but be vapor open in the summer. So preventing the wetting again in the winter, allow drying in the summer. On the right, we see a diagram of how this is working. The vapor variable smart membrane does not know the season. It's reacting to the relative humidity around it. On the left, we have the wintertime with the vapor drive going out. We have a roof on top with the membrane, the dotted line in the middle, at the bottom of the construction. We have average relative humidity around it of 40%. It's relatively high indoor humidity because it's an airtight, high-performance building, and it's vapor retarding at that humidity. In the summertime, on the right-hand side of the diagram, the vapor drive is inward, and now, if there's any moisture in that assembly, it is pushing down against the membrane, and is the highest point of humidity within that assembly. So as we get to high and dangerous levels of humidity, that membrane starts to open up and react to the humidity around it and allow it to dry inward, and thus building drying reserves. So here we see the vapor curve, if you will. How it's reacting to the relative humidity. On the left, the lower left, we're at very low humidity levels, and it's virtually vapor close. And again, as it's rising to 60, 70, then to 80%, where we're really in the danger zone, it opens way up. So it's reacting to this humidity around it. And this has great, great protective qualities as we're adding insulation. So we're looking at not just the membrane and not just the brick, but all the materials in the assembly, that the drying potential is so important. We need to look at really all the components going into it, all the vapor profiles of it, and make sure that that brick can dry outward. It needs to be able to dry outward. It needs to be able to dry inward. And we want to we're not only shedding the water outboard, but we're retarding the wetting from the inside. So now we want to insulate these buildings. Perhaps the most controversial sentiment, and we want to insulate them not just a little bit, we want to insulate them as much as we can safely insulate them. We want to make them as efficient and as comfortable as possible. And so for our exercise here, we're going to use some WFI simulations to show what is possible. We'd like to use WFI as an indicator. It's not a Bible. It's not a saying that definitively this is perfectly good and this is definitely a failure. We like to use it as relative risk indicators. If we add a little bit more insulation, how much risk is that adding? If we take a little bit away, if we have a different vapor profile material, you know, is this riskier or less risky? So let's take a look at a few examples. So we're going to take example of a historic masonry retrofit in Burlington, Vermont, cold climate, and we want to see what that the moisture level is at that red dot. We want to make sure that we are not going to have a mold problem at the inside face of the brick. So we are looking at a graph, a WFI graph, where we have the red is temperature and the green is relative humidity over the course of 5 years. So each peak in the red is the summertime, the dip in the red is the wintertime, and we see correspondingly in the winter we have a rise in the humidity level as the exterior, as the interior humid air is coming into contact with the interior face of the brick wall. In this case, we have 4 inches of fiberglass insulation and airtight drywall with no vapor control. And what we're seeing is that the wall is become saturated over the course of the winter and for an extended period of time. The green dotted line across is at about 80% relative humidity, and that is the line, again, looking at the ASHRAE 160P standard, is the line we don't really want to cross, or if we cross it in brief periods when it's really quite cold out. That red dotted line is the 41 degree temperature. These sort of bracket the mold danger zone. So the question here is, well, this thing is getting saturated every winter. Why don't more of these buildings built like this, which is a developer standard, show more damages? And the issue is that typically they're still full of thermal bridges. They're not that well insulated. They are full of air leaks, and they are still baking themselves dry. That the heat loss through the enclosure is enough to make up for the damages. Not always, and there will be damages, but that's sort of why it that occurs. So here we have now taken it and changed the insulation from fiberglass to cellulose. So it has some more hygroscopic properties. It helps moving, again, buffer the moisture levels, and so we've taken the plateaus off of those peaks. It's still going up to quite a high level of moisture, almost 96% in the winter, but clearly right in the middle of the winter. But it's still really too high for comfort at this point, and it's, you know, it's not that much insulation. It's only 4 inches. So now we have that 4 inches of insulation. We still have the drywall and board, of course, but we add the vapor variable smart control, which, as we see now, the humidity level, while it starts high because we're looking at initially moisture-loaded assembly, it dives down over the course of the summer, that first summer, as it's drying inward. And now in the wintertime, where the other ones were peaking much higher, it's preventing that moisture loading and keeping the moisture levels at safe levels. So we have a very dramatic effect with this smart vapor variability. So now we say, well, great, we're safe with 4 inches. Let's add more insulation because, again, we want to add as much as possible. So now we're at 6 inches of insulation. Now we're up, you know, getting close to 88% there. It's still a nice going down, staying in a safe trajectory. This may be okay for some folks' risk profile, what they can take. Other folks may say, no, I really want to keep it below 80%. So maybe, you know, 5 inches of insulation or 5.5 inches of insulation is going to be what does that. But let's go in the other direction and see what happens when we add even more insulation. Say, well, I accept much greater levels of risk, and we're not recommending this. We want to see what the effect is here. So as we're adding more insulation, we go from 6 inches to 8 inches. We're seeing the wetness, the moisture levels rise, just the phenomenon that we were talking about. And when we go from 8 to 12 inches, it's higher still. So we see the risk levels rising with the insulation levels. So the question always is asked to us, well, how much is too much? And we have the most unsatisfactory answer at Walls, that it's highly dependent on the situational specifics, that mold danger certainly precedes freeze-thaw danger. In most cases, the freeze-thaw danger can be mitigated, if not completely. Nothing is 100% drastically. And we want to use, if we have any questions, if we're trying to do anything sort of out of the ordinary, we use specific WFI modeling and again testing of the brick to see what constraints we want to stay in. The key thing here is as the R value increases, the air tightness and vapor control must too, because these are the leading mitigating factors against moisture damage. The windows, we like to say they should be passive house compatible. You've just done a great enclosure, they should be at passive house level. It changes the whole dynamic of living and working. Below grade, you know, it really depends on where you are, but we often see R20 as the upper limit because they're just quickly diminishing returns. And at the roof, we like to say put as much as you can. The sky is literally the limit. So once we've dealt with the basic areas of insulation in historic masonry retrofit, we want to look quickly at the thermal bridging. We would like to build thermal bridge free, but these masonry buildings have a ton of thermal bridges already built into them. Party walls, for example. And here we see in plan where they will return the insulation on the party wall to prevent the insulation from being short-circuited. In plan, this works pretty readily. In section, however, where if we were looking at a ceiling and a floor, it can become much more architecturally difficult. Here's a very nice example from the Building Science Corporation showing you know, continuous floor slabs that are intersecting the exterior wall, providing continuous thermal bridges. And when we have this kind of thermal bridge, we want to be careful not to over-insulate the enclosure because the thermal bridge is really bypassing a lot of the effectiveness of that insulation. And so the economics and the effectiveness becomes an interesting equation. What's often incredibly critical is where we're looking at joist penetrations of exterior walls. That typically uninsulated exterior wall with a joist penetration, like at the image at the top, it's quite warm. And it's, again, keeping itself dry in that way. It's not maintaining wetness. You often see, you know, where you have joist ends with wetness problems are typically like right at grade, where they are just relentlessly at elevated moisture levels. Here now, lower image, we've added insulation. It's colder at the joist end. The wood is obviously could help propagate mold growth, and so air tightness becomes even more essential in these locations. That we need to really, the air tightness is the primary line of defense to keep that humid interior air from getting to those cold locations. And here we have an example of a retrofit in Brooklyn, New York, showing the joists going through the air control and vapor variable smart membrane at the exterior wall. Thermally broken beam connections could be another thing, where we're actually pulling the joists and beams out of the wall. Here we see a steel beam connection thermally broken. And then we could also look at building a building, how do I say, build a building in a building. So you're pulling the structure all the way to the interior, and we're avoiding all thermal bridges in that way. So many levels of trying to achieve that. So with the insulation and thermal bridges in hand, great windows, very briefly, we want to note that they should be fully integrated. You could really sit in front of these windows without heating on a cold winter day and be comfortable. And we're very happy to see the development of historically acceptable windows. These are simulated double hungs that operate at passive house performance levels. We're integrating, this is a slide from our ebook and book, which is easily, you can download for free, which is showing the integration of the window within the historic masonry structure. You want to think of the window as being a continuous integrated piece of the thermal control, the air control, the vapor control, all of it. It's not a separate thing. With the air tightness and the enclosure in hand, we want to end on the note with great ventilation. You cannot ignore the ventilation. You can't have exhaust-only ventilation. You need to supply an exhaust. It is best when it's balanced and distributed. You're supplying the air to the rooms, the served rooms, and you're exhausting from the service rooms. We want to have high efficiency heat recovery. This is showing a central system. Or we also have the decentralized system that we spoke of at the top of the presentation, where you don't have ductwork. You can have high efficiency heat recovery and filtered fresh air through linked pairs of fans. So now we want to briefly flip through a case study, which is actually a couple of buildings mashed together, high performance retrofits, and show some on-site examples, some further examples of all the things we've been talking about. So the slab on grade, here we're showing mineral wool as a foam substitute below this the slab on grade that's going to go in afterward. And you can see that the mineral wool, the insulation is turned up the sidewalls, again, to prevent that thermal bridging, that short circuiting of the insulation. We see here the slab, in this case the plastic, the blue plastic is coming up from underneath the slab and is being tied into the masonry wall connections, where the masonry wall is acting as the air barrier, and this is the felt tape that's actually plastered into the masonry. The important thing with the slab and wall connections, with all of these where the different components of the building comes together, is that they be the flexible and will not embrittle over time. Floor and wall connections, and again, these are some of the illustrations from our book. How you go through the image on the right, you see the floorboards cut back, you see the control layers going up through from floor to floor, so you have that absolute continuity. Again, this image here would just add, just sort of this relentless idea of cutting back the floor. Here they removed all the floors and put the plywood back, but they held it back so that they could have complete access to the penetrations. You almost want to think about it like as if you were waterproofing a roof, where you need to get around the thing to make sure that it's all done completely well. Here we have a window installation, and we see the service cavity with the furring. So we have the control layer, and then we have the strapping that the chipboard is going to be applied to, and how that is that service cavity is accommodating the wiring, the outlets, the switches. So we're minimizing the penetrations and integrating the penetrations that we do have. And then finally, the roof and wall connection. Again, we want to have the continuity of the inboard air barrier across the roof to the walls to maintain that control. So in summary, we want to say that high-performance historic masonry retrofits boil down to these few things: that we need to successfully shed water, and that is the first, second, and third thing, really. You know, it cannot be more important. We want to maximize the air tightness, second most important thing, and along with that, the vapor control. And with those efforts fully in hand, we can really maximize safe insulation levels. We want great windows, and I seem to have lost my fifth bullet point, which is the great ventilation. So I think that that's it. We have the downloads available. I've mentioned to it. You can get them online for free, electronic, and we have CAD drawings that you could download for free as well. We have a hard copy that you can purchase. So please find out more at our website. We're active on Twitter and on our blog, and we hope to work with you soon. We hope this was helpful. So I don't know if there are any questions.
Hey, Ken. Yeah. Can you hear me?
Yes, I can.
Great. Yeah. We definitely got some time for questions here. We got a few piling up. Before we get to the questions, want to make sure everybody knows for continuing education, I'll be putting the GBCI number here in the chat box briefly. For those listening live, make sure to also take the survey that comes your way. Unfortunately, this one is not approved for FIA, so ignore that there. But make sure to take that survey. And then for those of you listening on demand, so not talking to any of you here, those of you listening to the recording session here in the future, make sure to complete your 10-question quiz with a 70% passing rate in order for you to get your CEUs. So, you know, two of the questions that were coming in, Ken, were focused on the warmer climates. So I don't know if you can see some of them here. I think, let me see if I can find something. Yeah, I mean, really, they're talking about, you know, hot, warm climates. There was one specific to Atlanta here. Is interior vapor barrier recommended for a humid southern climate like Atlanta? So what can you tell us a little bit about the humid climates?
Well, so this presentation is definitely geared towards the colder and mixed climates. So apologies for the hot and humid, but even Atlanta has winters, and what we see down to the Panhandle and even down as far as Gainesville, where we have a winter time, the dynamics are similar. What I would say is that everything we want to look at carefully and run simulations with it. Clearly, in a place like Atlanta, the freeze-thaw is not going to be an issue. I think it is safe to say. However, the mold issue and the moisture loading of the assembly is going to be the chief concern. So we've made, what we've seen thus far, we were actually looking at, and I could say this, we were looking at a building in Gainesville, Florida, a historic, a 4-story, pretty big brick building, and running the simulations on that with either mineral wool or cellulose inboard, and making a few assumptions with the smart vapor retarder inboard of that, it was still showing increased robustness and staying well within the safety levels that we would like to see. So it's certainly possible. Of course, there are microclimates, there's orientation, there's the level of the brick. There are a lot of ifs and buts in there that need to be nailed down. But I think we can say that this approach, while it's most clearly demonstrated in the colder climates, does work through the mixed and can work quite far south. Hot and humid, the true hot and humid, like the climate zone 1 in Miami, is a different animal altogether. Where you stop having winter time and you have the reversal, you stop having the reversal of the vapor drive, then it's another conversation.
Great, thanks, Ken. The question that come in from Diane here have you gone back to installations, say after 5 years or more, to see how the details you're describing are performing?
Yes, we have a couple of instances where we have data monitors logging the moisture levels, and we are seeing them act appropriately. We're actually in the process of installing a number of more projects now. We're sort of trying to get more and more focused on that. We do have data. It is limited real-world data, but we have some, and you know, we're encouraged that it matches up to the physics that the models understand.
Good. Question from David. What was the material used to thermally break the steel beam to masonry connection?
So that was isocorp shuck material. It's another company. We don't carry it, but it's a very cool. They have all kinds of structural connections where you have steel and other structural members. So it's a German company as well.
All right. And hey, Kristen, a question from her is, how does this work with requirements that insulation be in contact with the drywall? When there is a surface cavity, it seems this would create an issue with those requirements.
Yeah, if you need to have that, we can insulate the surface cavity. Oftentimes, folks would like to do that. Take mineral wool and fill the surface cavity with insulation if you need to. What's important there is that the primary insulation layer is outboard of the vapor control and air tightness. We like to see typically 75% of the insulation outboard. We've seen instances where it goes down to even 50-50, but again, it's one of those things where as it gets more risky, we want to look at it more closely and see what the data might be indicating, where things stand.
Sure. Great. Question from Samantha. Some historic brick structures in southwestern Wisconsin were constructed with 3 layers of brick with an air gap between the outer brick layer and the inner 2 layers. Can you discuss how this may impact drying out and insulation air sealing?
Yeah, well, it doesn't affect, I mean, it helps, I guess, it could. So, well, the first thing is we want to make sure that the masonry is in good working order, right? And with that said, with the repairs and repointing and everything, it should not have be that different than what we've been talking about with the solid 3-way brick building. It should be very much the same. Having said that, we want to look at the details and the penetrations. One can say, where the wood joists are penetrating 2 layers of brick in that interior part. What's the implication of that? So it's not as it's not immediately transferable, but one suspects that we have seen several different types of makeup of historic masonry, and working it out.
Great,
our
thanks.
gut would say that it would work. It should be able to work, but we don't want to, be cavalier about it. We want to get into the details.
Good. Well, we still have some time for some more questions, and here's a question from David, and I kind of wanted to. I'm glad he asked because I wanted to kind of get into the foundation questions. And so, David's question is there a way to get a capillary break in existing masonry wall at the grade level? And I guess I wanted you to discuss and address, foundation insulation, as I think it's starting to become more important, like in the Energy Star 3 program and other programs are looking at ways to insulate the foundation even for existing buildings.
Yeah. I mean, what we're seeing is so where we have the most experiences in urban environments, where you're truly insulating from the inside all the way, and that means in the cellar as well. And so we're typically, digging down a little bit to get back some of the headroom we're going to lose with the insulation and the new slab. They're often, putting drainage pipes, perimeter drainage around the foundation before and putting new gravel in and putting down plastic in the insulation slab. So that they're actively tackling the water and the moisture levels, the groundwater levels, from the way that they can. If you can get to it more easily from the outside of the building and go around the perimeter, by all means do it. And really, it's only an issue if it is an issue, to state the obvious, that if you don't see history of degradation of the water uptake from the masonry and the damage from that, it may not be such an issue, but certainly we've seen a lot of locations where it has been, and the capillary breaks important in terms of protecting, again, those wood joists, depending on how close they are to grade, and as well. It's really important whether or not those are going in, that the repointing, the sacrificial layer of the new mortar, the soft lime-based mortar, is there to do its job, to be sacrificial, and that like old Italian village, every decade or whatnot, you may need to update the coating. Does that answer it? In terms of insulation, again, if you can go from the outside, we want to insulate from the outside. What we see most of is from the inside, like we showed in the diagram, was with the Roxul below slab. That Roxul is now approved. We don't sell Roxul. It's approved below slab, the IS board. And it's a matter of turning it up. Typically what we see is mineral wool below grade and cellulose above grade.
So are you seeing, people actually, I guess you could say, busting up the slab to insulate it on quite a few projects?
Yeah. Oh, yeah. I mean, the folks that are going for passive house level performance or higher performance.
And I assume these are good opportunities to get in radon mitigation systems.
Yes, absolutely.
Good.
Yep.
All right, well, we've got some other questions here. Hello there, Keith. Thanks for joining us. 2 questions from him. Let's do the first one first. Can you talk a little bit more about some of the different modeling tools you're using that inform efficiency and cost benefits for your projects?
Sure. I mean, primarily what we see using, I mean, we're very passive house focused. So in terms of our core constituency, and then moving out towards folks who are concerned with just doing higher performance, and we certainly like to work with a spectrum of designers, contractors who are just trying to do each project a bit better and a bit higher performance. But when we're starting at the energy modeling, typically is going to be the passive house planning package that goes with passive house designing. And there you're trying to hit, very specific energy use metrics, and you're trying to do it in an affordable way. I would say we're not doing in-depth scientific calculations as to payback for these jobs. There are definitely rules of thumb, and there are examples out there of different results. What we're doing is more based on the experience, what we see happening with the modeling and the results out there, what needs to be done, finding sort of the best practices, what's essentially the most cost-effective approaches regarding materials and labor to get very high results. And at the end of the day, what we're concerned less on is having, the most cost-effective solution. I mean, we want it to be cost-effective. It should be affordable. It should not be a crazy amount of money. It needs to be defendable. But could you save a couple of more dollars and done something else slightly differently that wouldn't have had such an impact on the performance? Maybe, but we're trying to come up with a set of tools that, again, that you can apply much more broadly and get to a good result. So, and so in terms of many of the projects aren't using energy models, but we have this toolkit that we see from experience, and we can apply that toolkit and know that they're going to get, if not the most optimized result, a very good one that's affordable. I hope that, admittedly that's a vague answer, but it really is sort of the approach of it.
All right, and we got one last question here, and that is, do any of the particular products you work with that you know of or maybe heading in this direction, have they been declared? So that is, for those of you who don't know, Living Building Challenge encourages many of its products to get the Declare label, or now I think they have a brand new Living Products Challenge that actually brings in a third-party verification to ensure materials are all the way from being, regionally sourced to having avoiding some of the 12, I believe it's the red list, some of the most worst-in-class chemicals, as well as having the recyclability reuse component to them. So Ken, I guess, large question there, but do you know any of them that you work with that are pursuing some of this sustainability manufacturing certification?
Yes, absolutely. I'm so glad to have the question. I was remiss in not bringing it up in the presentation. It's something that the whole sustainability issues in general we're very cognizant of, and particularly toxicity. And so some of the core products that we have, the tapes and caulk and membrane, all have the Declare label already. We were very conscientious about applying for that, and wanted to achieve those. And the red list and all of that we are very conscious of. So I guess I could say now that the material Intello, membrane, the Vanna tapes, and the primer RP are Declare, and we're going for more, and the Havelock wool as the Declare label. So yes, we're very appreciative of that and want to keep pushing it.
All right. Well, I definitely want to thank Ken Levinson here of the High Performance Building Supply for joining us here on our second session, and we hope to have I believe there's a lot more topics we can talk about together, so hopefully we'll have you back out. Ken, just real quick before we wrap up, where can people find more information?
Yeah, so please go on to our website, which is 475.com, and that's spelled out FOURSEVENFIVE.com. Or you could email us at info@475.com, or myself personally at ken@475.com.
All right.
Thank you.
Thank you, Ken. Thanks, everybody. Take care.
Thank you so much. We very appreciate it. Bye-bye.